My name is Thijs Masmeijer. I'm doing the PhD program at the University of Washington, the Aeronautics and Astronautics Department. I'm just starting the fourth year. I'm hoping to graduate around spring and summer. We'll see. I did my master's and bachelor's in the Netherlands. That's where I'm from. I decided to join the Illimited lab here at the department, which is a bioinspiration lab that focuses on structural vibration. That's where we set up the project that I'm going to be talking about today with you guys. So, spiders, when they build a web, the web is not just used for catching and retaining prey, but it also has a very cool multi-functionality. Maybe that's a word not for a 5-year-old, but it has more functions than just the one you know about. What a spider actually does, it's while it's sitting in the hub, which is like the center, it's feeling the vibrations in the web. And then based on that vibration, it can predict where in the web there is prey and impact. And then based on that vibration, it knows where to walk. So this is I think that's a really interesting phenomenon. And what biologists think is that a spider web is designed in a way to make that predicting the location as efficient as possible. So what we are interested in is how does a spider design a spider web to make finding prey as easy as possible. So we are interested in what designs help spiders with signaling. So when you actually look at spider webs, and I didn't find this is from literature, is that spiders design their webs to be asymmetrical. So what we mean by that is that if you take, I don't know if you can see this, but if you look at a spider web, you can see that the place where the spider sits, the hub, is not in the center of the web, but it's above the center, which is what we call eccentricity. So when we found out from literature that design is important for signaling and that spiders design their webs asymmetrical, we wanted to find out whether these asymmetries help spiders. So when we started this project, we started with investigating the dynamical properties of spider webs and see what effect this eccentricity has on the dynamics. So we designed spider webs with various levels of eccentricity, and what we found is that the natural frequencies, the frequencies that a spider web is vibrating in, the differences become larger if a web becomes more eccentric. And the suspicion that we had is that when these differences become bigger, that it becomes easier for a spider to measure them and base decisions on them. And this was all done numerically, so just the spider web in the computer. But this is, for us, was the first indications okay, we want to explore this phenomena more deeply. And that's where we actually started to build these webs. You want me to just continue?
If you want, yeah.
Yeah, so in the end, we are an aeronautics and astronautics department, and I'm looking at spider webs, so it's a really valid question to ask, why do the engineers care? So not just spiders are interested in signaling, in impact localization, but in engineering you can think of many applications as to why you would want to have better signaling. One would just be impact localization on aircrafts for, yeah. But another cool application is also structural health monitoring. So that field places sensors on a structure, and based on the signals that you measure, you can make a decision or you can make a prediction of whether your structure is damaged and where it's damaged and how damaged it is. However, the design approach for such sensing systems in engineering is right now very different from what spiders do. So what we want to investigate is what are the differences between how spiders design signaling systems and what we do in engineering, and then maybe we can learn something from the spider and apply it to engineering. So in that line of reasoning, there is one specific approach or one specific insight that we want to build more of this work on, and that's in engineering, what we usually do is we take a structure, a bridge or an aircraft, and then we find out where on this structure we should place sensors to make the signaling algorithm work as best as possible. It's called optimal sensor placement. So when you think, okay, a spider is doing this too, but the spider is always sitting in the middle waiting for prey to enter the web, and the places where a spider can sense is on like small little hairs on its legs. So it can kind of change where it puts a leg, but it's very limited in where it places it due to, just the size of its body. So it can just decide to sense here, 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 and here, like what we can do in engineering. So that's a very interesting limitation that a spider has, and it needs to find a way to overcome that. And that's where you come back to designing a sensing system as a spider, is instead of changing your sensing locations, you change your whole environment around you. So that's where we come back to why we are looking at different designs of a spider web, is where in engineering we only change where we put a sensor, but in nature you change your whole structure for sensing. And that raises the question, how should you change your structure? And that's what we're trying to explore. So when I came 3 years ago to this lab, we started this lab together with my advisor and my other PhD co-worker, Bart. And when we started, we just had a vision about we are interested in structural vibration and in bioinspiration. And then me and my advisor, Ed, we started just looking at spiders in general and just try to find something that is interesting to us. We looked at all kinds of things in spiders, like the microstructure of spider silk, which is kind of incredible. But then in the end, this project really started rolling when we found this biology paper that that made the claim that a spider web operates as an extended cognition of the spider's central nervous system. So that means that with an extended cognition, what they mean is not like a web is actually thinking, but that a spider is exploiting the web to help it with decision making. So from an engineering standpoint, that would mean that a spider designs a web in such a way that it makes extracting information from the web as efficient and effective as possible. But like, this is from a biology paper, and like, they're not thinking about what implications that has on design and on sensing. They just make observations from nature. And then when we read that from like an engineering standpoint, we really thought like, okay, we should start looking at what makes a spider web an extended cognition of the spider's brain. And then, yeah, that's the start of it. I'm very happy with the recent achievements actually. So we found out that our submission to mechanical systems and signal processing was accepted. And this is a journal that does not necessarily care about spiders, but it does care a lot about dynamics. So when we did experiments last year in Slovenia at the University of Ljubljana, where I got to work with some really inspirational people from the LADISC lab, we did the tests, and then we had to develop a novel motion tracking algorithm in order to characterize the vibration of these webs. And a publication came out of that, and then I'm very, very happy with that.